What is up, guys? This is Mr. Jones again. Today we're going to talk about geometric sequences or exponential functions. So you can see that on the screen already. I wrote them together. A lot of times they're interchangeable. So just like arithmetic and linear are interchangeable, geometric and exponential are also interchangeable. So take a moment, pause if you need to, but look at this pattern. And the very first question is going to be to describe and label the pattern of change you see in the sequence. So this is the exact same question that you guys answered with the arithmetic sequence, but obviously this is not arithmetic anymore because we're going to just review a little bit. So how can you describe the way you see the dots growing? Okay, so a lot of you guys probably saw it different. It's really hard to do that here online because we're not talking and sharing those things, and it's more awkward. So the way I saw it is I just saw it growing in this way. So I saw one dot obviously in the very beginning on three different corners, kind of like a triangle, if you will. So I saw one dot in the beginning, and then I saw it grow. That one dot added one dot. Okay, so I added it to the side, turning into two dots. So now the original was these two bottom dots, and then I saw it grow on the top. So I saw it grow on the side, the top, back to the side, and then back to the top. Is just kind of how I saw it. So everyone could have seen it a totally different way, and I hope you did see it a different way. But the main thing is that you see it growing, and you probably also see how much it's growing by, right? And so most people realize that it's doubling. And doubling is the exact same thing as multiplying by 2, right? So every single time, that's usually what students say, oh, I see it doubling. So the next question, I don't expect you to draw it because it's a lot of dots, but draw it if you must. But assuming the sequence continues in the same way, how many dots will there be at 5 minutes? All right. So hopefully you guys have an answer. And hopefully at this point you already drew a table. So you guys should know by now that we're going to want to make a table. So go ahead, pause the video, and draw a table that's related to these dots. And I'm going to draw a table, and I want you to see how close your table is to mine. Hopefully you can draw a pretty nice table. So go ahead. All right. Hopefully you have yourself a nice table. Don't forget, on a table, you always have to define your variables. So if you don't define your variables, then literally the numbers mean nothing. But if you define your variables, then someone can read your table and know what the heck it's talking about. It's not just some random table. So the x side is going to be just like the other problems, where we're basically going to say, okay, this is changing every single time by the same amount. So those are obviously our minutes. That's what's causing the dots to change. So the minutes happen no matter what. That's your independent variable. All right, your dependent variable, or your y, or in this case we just called it f of x. So hopefully you're familiar that y and f of x are interchangeable. What is this going to represent? What's in your table? Hopefully it says number of dots. Cool. So since it does, at 0 minutes, how many dots? At 1 minute, how many dots? How many dots? And you just keep going. And hopefully you don't actually have to count the dots, because we already talked about one really important thing. Let me get this stinking thing off my screen real quick. We talked about one really important thing, and that we are multiplying by 2 every single time. So since I knew we were multiplying by 2, once I knew the first couple, I just keep multiplying by 2. 6 times 2 is 12. 12 times 2 is 24, and so forth. So this should answer your next question, or the question you answered before. Now you know you're going to get it right. The answer was 96, right? How many dots were there at 5 minutes? There's 96 dots. Okay. So with that being said, I'd really like you at this point to pause the video. I don't want to put another question in here. So pause the video and take your time and do it. I'm looking for the explicit formula and the recursive formula that represents these dots. So if you can do that, pause the video. If you're thinking there is no way I'm coming up with those, then I guess just move forward. But it's always in your best interest to pause and give it a shot, because doing it yourself is where you actually learn the most. So do what you got to do. All right. So here we go. I'm just going to talk to you about recursive and explicit really quick. So let's put it in red, I suppose. Okay, recursive is always talking about what comes next. Recursive is what comes next. So if you didn't know that, write that in your notes. And that's always the one that has the f of x minus 1 in it. So it looks like this. Okay, remember, this is my now term. This is my previous term. So my now term, I'm going to put a box here so we can solve for it, right? My sixth term equals my x minus 1 is the previous term, so my fifth term. And what are we going to do to the fifth term, or 96, to get the next term? Well, we're just going to multiply it by 2. So that right here is the recursive equation. And this right here is whatever the heck I was multiplying by every single time. It's called my common ratio. It's called my common ratio, but I just like to tell kids, hey, just remember it's whatever the heck you're multiplying by every single time. All right, so there it is. You're just basically taking your previous term, multiplying it by your common ratio. I know the recursive formula was difficult for a lot of students last year, and it always kind of is. But really, that portion, the f of x equals f of x minus 1 portion, that portion never changes. It always looks like that. All right. The next equation is the explicit equation. Here's the form. If you have an exponential geometric equation, this is the form that we always talk about, a times b to the x power. This is the form. Okay, I put it over there because that's always the form for geometric exponential function. It looks like that. And here's the info. If you guys forgot, this is my y-intercept. And this is my common ratio. And what is common ratio again? Whatever the heck I'm multiplying by, right? So with that being said, this is what I was telling students about in the arithmetic problem whenever I said, go back to your video and see where Mr. Jones gets the numbers in the table to plug into the equation. Where is he getting those numbers? This is where I'm getting them, so pay attention. Wake up. Now's the time. All right, check it out. The y-intercept, where the heck is that? I'm going to put that in gold right here. This is my y-intercept, my 0th term, specifically this number. Okay, that's the number we care about. Excuse me, that's going to be the a value of my equation. So that says a times b to the x. My a value is 3. That is my y-intercept. Okay. All right, the other piece of information that you can see in the form is your common ratio. So I'll put a red box around that. I want you to see that. That literally goes to your b. So what is my common ratio in my table? Common ratio, look at me, circle it. Do you see it in my table? What is it? Ooh, it's a 2. Good. So 2. And then the last thing is just put the x in there. Look at this. This looks exactly like the form that I drew over here, right? Looks just like that, but I have numbers, and that's where the numbers came from. That's where they always come from. Okay, and sometimes, just so you know, it'll be written like this. Okay? So these two things are the exact same thing, these two equations. All right, guys, there you have it. You have an explicit equation. You have the recursive equation, your table. You have everything you need right here for this problem. See you next time.